Good morning, students. Last time we have seen or we have started the bonding theories of bonding in complexes, in which we have seen or we have started valence bond theory. In valence bond theory, we have seen the formation of octahedral complex and tetrahedral complex. Now we are going to see formation of square planar complex. Now the example for the formation of square planar complex is formation of NiCN4. Now in this complex, the atomic number of Ni is 28 and the oxidation state of this Ni in this complex is +2. Now here, valence shell electronic configuration of Ni2 plus ion is 3d8, 4s0 and 4p0. Now we can write this electronic configuration like this: 1, 2, 3, 4, 5, 6, 7 and 8. Now there are two unpaired electrons in 3d orbit. 4s orbit is vacant and 4p orbit is also vacant. This is the valence electronic configuration of Ni2 plus ion. Now the number of ligands which donate electron pair to the nickel during formation of this complex are 4, and therefore the number of vacant orbital of metal ion required to form metal ligand bonding should be 4. That is, here for the formation of this NiCN4 complex, this Ni must require, or Ni2 plus ion must require 4 vacant orbit, and here this complex is with square planar geometry, and during square planar geometry the metal ion should undergo dsp2 hybridization. Now here, during the formation of complex, these two unpaired electron undergo pairing, and that is Ni2 plus ion undergo dsp2 hybridization. Now during formation of complex, these two unpaired electrons undergo pairing, that is, two unpaired electrons present in 3d orbit undergo pairing. Now here these 3d electrons Ni2 plus ion undergo pairing, and the configuration becomes, now look here, all electrons, unpaired electrons undergo pairing to form 3d8. Now this 3d orbit becomes vacant. This is 4s0 and this is 4p0. Now here this one 3d orbit, then one 4s orbit, and these two 4p orbits of this Ni2 plus ion undergo hybridization to give 4 dsp2 hybridized orbital. Now these are 3d orbit which possesses 8 electrons, and here formation of these 4 dsp2 hybridized orbitals. Now these are vacant orbitals. Now 4 multiplied by 2 electrons of Cn minus ion donates its electron in this dsp2 hybridized orbital to form metal ligand or nickel and Cn minus metal and ligand bond. That is, 4 metal ligand bond are formed. That is, 4 nickel Cn bond are formed to form NiCN4 complex. Now this complex have geometry square planar. This is the geometry of NiCN4, and here in 3d orbit the number of unpaired electrons are absent, and therefore this complex is diamagnetic in nature. That is, number of unpaired electrons in 3d orbit are absent, and hence the complex is diamagnetic in nature. In this way, during formation of NiCN4, Ni2 plus ion undergo dsp2 hybridization to form 4 vacant dsp2 hybridized orbitals, and then ligand, that is Cn4 ligands, that is Cn minus ion, donates 8 electrons to the metal ion to form NiCN4 complex. This complex have geometry square planar, and there is absence of unpaired electron in 3d orbit, and therefore it is diamagnetic in nature. Next point we are going to see limitations of valence bond theory, in which first limitation that it does not give the explanation about high spin complex and low spin complex, or in other words it does not give explanation about strong field ligand and weak field ligand. Now in case of octahedral complexes we have seen that some complexes are high spin complexes and some complexes are low spin complexes. Now we have seen that in case of low spin complexes, the 3d electrons or d electrons of metal ion undergo pairing, and in case of high spin complexes, these 3d electrons does not undergo pairing. Then it does not, this valence bond theory does not give any explanation about this. Then second limitation, it does not give any explanation about the colors of the complex. Now here these coordination compounds have some color, or in aqueous state they shows coloration. Why this coloration occurs? This explanation does not given by this valence bond theory. And third limitation is that the geometry of the complex. Now we have seen that according to valence bond theory we can predict the geometry or structure of the coordination compound. But on the basis of experimental study, these structures are different from that of the valence bond theory. And due to these limitations of this valence bond theory, next concept or next theory is accepted, that is crystal field theory. This crystal field theory gives explanation about the geometry of the complex, then gives the explanation about high spin and low spin complexes, or what is meant by strong field ligand or weak field ligand. Also it gives explanation about the colors of the coordination compound, and therefore this crystal field theory is widely accepted. Next point we are going to see applications of these coordination compounds. Now in which first we are going to see first application in biological field or in biology. Now most of the complex compounds which are naturally occurring plays an important role in biological processes. For example, chlorophyll, which is a complex of magnesium which is used in the process of, or which is used by plants in the process of photosynthesis. Second is hemoglobin, which is the complex of iron which is present in the blood or in human blood in used to carry oxygenated and deoxygenated blood. Now next in medicines. Now most of the complex compound used in or applicable in the medical fields. Now here first is cisplatin. Cisplatin is the complex of platinum. This cisplatin is used in the treatment of cancer. Then next EDTA. EDTA or ethylene diamine tetraacetate. It is the hexadentate ligand which is used in the treatment of lead poisoning. Now next we are going to see third is to estimate hardness of water. Now the hard water consists of salts of Ca2 plus ion and Mg2 plus ion and Mg2 plus ion. Now here this EDTA forms stable complex with Ca2 plus ion and Mg2 plus ion, and therefore this EDTA is used to estimate the hardness of the water. Now we are going to see last application of this coordination compound. Now these coordination compounds are used in electroplating. Now these coordination compounds when undergo dissolution dissociates to small extent and furnish a controlled supply of metal ions. That is when these coordination compounds undergo dissociation to small extent and furnish a controlled supply of metal ion. Now these metal ions, when reduced, clump together to form the cluster of non-particles. Now when the coordination complexes are used, the ligands in the complex keep these metal atoms well separated from each other. Now therefore these metal atoms tend to form a protective layer on the surface. Now here therefore certain cyanide complexes of gold and silver, for example this is KAgCN twice and this is KAuCN twice, that is this is potassium dicyanoargentinate 1 and this is potassium dicyanoaurate 1 complexes. These are used for the gold and silver plating on the ornaments. That is when these complexes undergo dissociation. They undergo dissociation in small extent and furnish a controlled supply of metal ion. Now here this metal, that is this silver or gold metal ions, when reduced, clump together to form the cluster of non-particles. When the coordination complexes are used the ligands, that is this cyanide ligands in the complex, keep the metal atom, that is silver or gold, well separated from each other. These metal atoms tend to form a protective layer on the surface, that is surface of the ornaments, and therefore these two complexes are used for gold or silver plating on the artificial ornaments. These are the uses or applications of coordination compound, and here we have completed the topic, that is topic number 9, coordination compound. Thank you.